Thank you. Thank you very much for sticking around after it's sort of like intimidating to follow Wes, but thank you for sticking around for my talk. Let's see. This does not seem to be working now. My name is Rebecca. I am a data scientist. I live in DC, so I am here in town just for the rest of the afternoon, and then I'm flying back to DC where apparently it's snowing. But I work as the head of data science at a small startup that does digital media analytics in DC. But I am also one of the co-creators of the Yellowbrick library. And there was a talk yesterday about Yellowbrick that some of you may have attended. Benjamin Bangfort, who is the other co-creator of Yellowbrick, delivered that talk. And so this talk is not really a Yellowbrick talk, but Yellowbrick sort of makes an appearance towards the end, so you'll see. I think it will sort of make sense when we get there. But this is really a talk about the other thing that I do, which is text analytics. And so some people may have seen the Fox book, so it's a little hard to see with the light coming in. But this is a book that we published this past summer. It's one of the O'Reilly, animal books, and it's called Applied Text Analysis with Python. So this talk idea sort of is something that I started thinking about when we were working on that book. And it seemed like it might be kind of a timely thing, and it's interesting because today was like NLP day. At the conference, there were a bunch of NLP talks. So this is going to be an NLP talk, but with a little bit of a visual analytics twist. So this talk is listed as being like novice level, so I'm not sure how many of you actually would consider yourselves novices, but I'm going to just do a little bit of vocabulary and review in the first like 3 or 4 slides, just to make sure everybody's on the same page. So just kind of to make sure we all agree about what is what are we doing when we're doing machine learning. We have, some number of samples of data, and those samples are represented by, many numbers probably. And what we want to do is train a model that can learn things about those samples and make predictions about new samples that it hasn't seen yet. But if we kind of take a twist on that and think about how we would interpret that spatially, what machine learning really is, given some bounded, decision, very high dimensional probably decision space, how do we define regions of decisions? How do we carve up that space to serve up predictions for points in that space and points that can be projected into that space? In terms of vocabulary, the words, this is the language that I'm going to use. I know there's variation sort of across different machine learning communities. But the way that I sort of talk about these kinds of things is I'll talk about, instead of samples, I'll say instances. So those are, our points. And those instances are composed of features. And so if we're thinking about, a data frame or, a table, the instances are probably the rows, and the features are the columns. And that is what's going to make up our dimensions. So the feature space is the n-dimensional feature space where those variables live, and feature extraction is the kind of that process. And here I'm calling it an art because I think that this is sort of why data scientists are still necessary, because there's this kind of immense amount of effort in creating features that actually will be predictive. So it's that art of creating the decision space to make the predictions. So, really simple example is, let's say we want to make, predictions about how thick a car tire will be after a set of timed trials. And maybe, our columns here are the features that we know about are how far the tires had to travel during the test. and how long the test was, and maybe how much of a certain kind of chemical preservative is introduced into the tires to keep them from wearing down too quickly. So in this case, we have a how many dimensional feature space? Right, three-dimensional feature space. But we probably have this sort of intuition that distance and time by themselves might not be enough, right? We might have this sort of intuition that how fast the car was going will have some influence on how quickly the rubber kind of burns down on the tires. And so we're going to do feature engineering. We'll generate another variable that accounts for speed. And now we have a new feature space, right? So we have this sort of phi mapping between our original feature space into our new feature space. So can this be done with non-numeric data? It can. So who in this room works with other than numeric data, like text data or video data, audio data? Okay. So, a lot of, most data, right, is sort of maybe not coming at us starting out of the box numeric. And so we're going to require some sort of transformation so that we can do machine learning, because in order to do machine learning, we have to have numbers. And so the trick is, when we're doing that transformation, distance is sort of not always a straightforward thing, right? So when we're looking at the distance between two tires that are represented in terms of the speed at which they were tested and how far they traveled and how much chemical preservative, there's a kind of a maybe intuitive sense of how you would define the distance between any two tires in that training data. But with documents, let's say, or videos or pictures, how do you make that decision about how to decide if two pictures are close to each other in space or far apart? Or, how do you decide if two documents are similar, right? Because that's sort of that's what distance means when it comes to documents. So there are a lot of different ways to measure distance or sort of define similarity. The default, so users of scikit-learn, show of hands, probably most people here. The default distance measure in scikit-learn is what? So it's usually Euclidean, right? Unless it's changed recently, but I think that's usually the default. And the kind of common mantra, rule of thumb for text data is to use what kind of distance? To use cosine distance is sort of the popular choice. And sometimes cosine distance is the right choice. But there are, just the way that there are a lot of different, estimators in scikit-learn, and there are so many estimators, and Benjamin talked about this in his talk yesterday. There's so many different estimators to choose from that, it doesn't make sense not to try them all. You should sort of try them all, especially if you have a new data set that you're not familiar with and you don't kind of have an intuition about what kind of model will be most performant. It's sort of similar with distance. If you are working with a new data set that you're not very familiar with, a new text corpus, let's say, that you don't know very much about, there's no reason not to sort of experiment with, several different distance measures to see which one is going to be sort of most effective at helping you, generate predictions. So scikit-learn has a bunch of options, and actually most of the options in scikit-learn are actually SciPy options, and there are a whole lot of them. Not all of them sort of make sense in the context of scikit-learn estimators, and a lot of these don't support sparse matrices, so that's something to consider. But this is just sort of kind of a illustration of how many options there are. So all of these options that you're sort of maybe not considering if you're just using the default of what's in scikit-learn. And for text in particular, which is what I work mostly with at work, our choice is going to be really, really important. And the reason that it's going to be really important is because a couple of things. One is that text is extremely high dimensional. And essentially what you end up with is a dimension for every word in the entire corpus, so across every single document. And if you're doing feature engineering and doing things like bigrams and trigrams, those are more dimensions, right? So this is extremely high dimensional. And it's also going to be very sparsely distributed, right? So for most of the documents in that corpus, once we've kind of created document vectors, most of the values in those vectors are going to be 0, probably, right? Because words are not going to occur in every single, the same words are unlikely to occur in every document. And the words that do occur in every document are probably not very interesting or informative. So some of the features are going to be a lot more important to us. So the example here is, let's say we're trying to cluster sports articles in a corpus of hobbies, documents about hobbies. The of dimension is not as important as the basketball dimension, but they both get a dimension. So that's kind of tricky. And then some feature variations are going to be more important. So if we're trying to differentiate, between a bunch of different kinds of books, and some of the books are math books, and some of the books are horticulture books, the frequency of the word tree is maybe not going to be as meaningful as the frequency of the word horticulture. And that's because tree is going to appear probably with fairly great frequency in both kinds of books about, because tree means something different in math books, but it occurs in math books also. So what do we do? How do you make the sort of decision about which distance measure is going to work the best? So here's one option that I propose to you. So what I would recommend is that you consider using something like stochastic neighbor embedding, or maybe UMAP, or one of the variations, maybe a manifold visualization. This is an example of something from the Yellowbrick library. So you can do kind of like a one-line, use a one-liner to generate this, which is nice because you can do kind of like rapid prototyping and do quick analysis and get that kind of visual feedback. But what's happening here under the hood in Yellowbrick is that by default we're doing a dimensionality reduction, and then we're kind of embedding those original points into a space using probability distributions from the reduced space and the original space, and then doing a simple 2D scatter plot. But what you get from this is you start to see patterns in the corpus. You sort of see the distribution of the documents. You can sort of maybe start to see that maybe certain documents are kind of clustered together. The yellow documents here, which are the sports documents, are kind of fairly closely clustered. There are other classes that are pretty diffuse, pretty spread out. So we already know that that's probably going to be a harder category to classify, unless we do some special feature engineering or feature extraction. So this gives us a lot of information. And what's kind of neat is that you can pass in different distance measures. I just showed you all the ones from SciPy. You can pass in different distance measures into your t-SNE plot and see how it changes. And so I was going to show you a couple of examples. So the data sets, I wanted to try this with a few different data sets. These are all data sets that you can find easily. So the second two, the farm ads corpus and the dresses attributes corpus, are both from the UCI machine learning repository. And the first one, the hobbies corpus, is one of the data sets that ships with Yellowbrick. So you can kind of easily get that. So the three data sets are all really different. They're all text corpora. But they have a lot of variation in terms of, max doc length, min doc length, and how many documents are in the corpus. And so this gives us a chance to kind of examine across several very different corpora what the effect of different distance measures is going to be. So we'll start with Euclidean, right? So this is straight line distance. And the way that we are going to make this happen in Yellowbrick is, you import, from Yellowbrick, you'll import the tsne visualizer, and it has sort of that same API style as scikit-learn, so it's sort of familiar. You instantiate it and you pass in, keyword argument, and you say, I want Euclidean distance. In fact, this is what it will give you by default, even if you don't pass in, a keyword argument. But here, just to be explicit, we're saying, okay, now fit the tsne visualizer on my documents, and we know the labels in this case. And so color the classes with the labels that I'm passing you. And then what we get is, I think extremely different results for the 3 different corpora. So the hobbies corpus, which again is a corpus of documents about like sports and politics and stuff like that. So you can see that the tsne plot is in some of the classes there's some clustering, but it's not particularly helpful. Like you don't have a clear sense that this is going to be something that's going to be easy to do classification on, right? You don't have these sort of really satisfying tight dense clusters. It's fairly distinct, the 2 classes in the ads corpus. And for the addresses corpus, it's a little bit of a blender, right? So you can maybe see some structure there, but it's not obvious that Euclidean distance has sort of done us any favors. So why don't we try, a few other distance measures? So if we pass in metric equals city block, right? So this is going to go and get city block algorithm from SciPy under the hood on your behalf, and it's going to give you a representation of distance between documents as the sum of the absolute differences between the 2 points, which are both instances of documents in the corpus. So this one, I think, has a very different kind of effect. This is, these are not terribly different distance measures, but you can definitely see, I think this one is, the hobbies corpus is, I would feel much more confident about trying to do classification on the hobbies corpus after seeing this version of the plot compared to the one that we saw before with Euclidean distance. And the ads corpus, again, is, there are two fairly distinct clusters, and the addresses corpus, again, is like a little bit of a mess. There's a single cluster that the green points, that's maybe a little bit, distinct. We can do chessboard distance by passing in the keyword argument Chebyshev. This is, a special case of Minkowski distance, the L infinity norm. This one I think actually does better with the addresses corpus, which I think is sort of interesting, but maybe worse with the ads corpus. Here's another generalization, Minkowski distance, which is another popular choice for people who use scikit-learn. I think a lot of examples you'll see people kind of manually selecting to use Minkowski distance for their machine learning problems. This gives us, I think a very successful clustering result for the hobbies corpus, and probably, slightly, again, kind of a mess with the ads and addresses corpus. Mahalanobis distance here, so this is going to be, a way to rescale the original coordinates with respect to the distribution of all of the documents. And here we have to, in addition to passing in the keyword argument for the distance measure, we also have to pass in method equals exact. So this is a scikit-learn thing. I feel like this is, a really interesting kind of result here. You sort of like kidney shape, but it's very distinct, that you don't get that sort of same distinction with the other distance measures. So hopefully you're sort of starting to see that it's pretty cheap to run a single line or two and test out different distance measures. It doesn't cost very much, but you may end up with kind of a very effective way of, before you actually, ahead of machine learning, before you try to do classification, let's say, a very effective way to kind of get a sense of whether or not your distribution is going to suffer from, diffuse classes, or maybe like even a situation where there are two classes that are, on top of each other, and that maybe classification is not going to be possible without significant effort. Cosine distance is, the popular choice for text, but, I think what's interesting is that it's not always the best choice, as you can sort of see from the stochastic neighbor embedding here. Just a couple more. This is really just, maybe a little gratuitous at this point, but just to show, it's so easy to kind of explore a lot of different distance measures before you kind of head towards the classification stage where you may, unknowingly be hurting yourself, be impairing your model by selecting a distance measure that's not appropriate for your data set. What do you think Jaccard distance will do? So Jaccard is a set distance, so it's very different from metric or vector space. So any intuition? It's a mess, right? And so is Hamming distance, which is, I added these two because people generally will ask about different kinds of set distance or edit distances because these kind of come up when you're talking about text analytics. But it's another just good example of how there's not sort of a one-size-fits-all distance measure. You have to really make very specific decisions on a per corpus basis because you could end up with a distance measure that's not good at all for you. So in the last kind of couple minutes here, I want to kind of give you a sense of how I think that, that kind of feature exploration would fit into sort of a more complete analytics pipeline. And so I'm sort of thinking of this in terms of what they say, Schneiderman's mantra. Ben Schneiderman is a professor, emeritus professor, who did a lot of research into visual analytics. And the Schneiderman mantra is overview first, zoom and filter, and then details on demand. So the Yellowbrick kind of workflow is really perfect for this because it offers tools for feature analysis, for model algorithm selection, and for hyperparameter tuning that let you kind of have that high-level overview of a data set or the performance of a model, and then zoom into kind of a particular class to see how a particular class is performing, or how a particular feature is related to another feature if they're covariant or something like that. So here's maybe an example of what you might do. So let's say we have a new data set. We go through kind of a bunch of t-SNE plots. We get to a point where we feel fairly confident about our distance measure. And we've got this sort of, we're asking questions like, what is the overall shape of my data? Are there discernible patterns? Do we think we can classify this? And once we feel like the answer is yes, maybe then we do, this is a lexical dispersion plot behind me here. And the question you're asking now, right, so now we're going to zoom in on a few words. And so that's what we've got here. We're going to look at the occurrence of a few specific words across all of the documents in the corpus. And so we'll be able to see their frequency. And if they are associated with certain kinds of documents, the gray dotted lines there are document boundaries. So you can also use this to see, are these words that are occurring in documents that are particularly short or particularly long? Because those are also things that can impact modeling. So here's another example that doesn't use t-SNE. But we have another visualizer in Yellowbrick that does intercluster distance mapping. And so another example of this sort of like overview first, zoom and filter details on demand is maybe to start with an intercluster distance map where we're asking questions like, basically, did I pick the best K value, right? Did I pick the right number of clusters for my documents? Because we will know that we've picked a good K if our clusters are very separate from each other and very dense. And you can kind of very quickly and intuitively see that with the intercluster distance map. And then once we sort of feel confident about the K, right, so we've tried a bunch of different K, we've done a bunch of these plots, now we're confident about our K, now maybe we'll dig into each of the clusters, the resultant clusters, and do something like a token frequency distribution and try to see if we can figure out what the most informative features are for that cluster. How would I predict that a document was going to be assigned to that cluster next time based on the most, the kind of most informative words, or potentially, am I in a situation where I have a lot of stop words that need to get filtered out? In which case, you can kind of do the cycle again, filter out stop words, do another token frequency distribution, and then start to see what those most informative features are of your documents. So, I'm going to wrap up here with a plug for Yellowbrick, not just kind of to use it and kind of dive in. In fact, I hope all of you, if you haven't already, if you would visit the repository and give us a star, that would be wonderful. And actually, we just became a NumFocus affiliated project, and so if you go out to the NumFocus sticker table, there are Yellowbrick stickers there that have the URL of our documentation. But I would, strongly encourage you, if you are interested, if you feel sort of inspired by Wes's talk about kind of building something open source together. One of our sort of aspirations as a library is to be, the best place in GitHub, in the open source community to give your first contribution. We're very, very welcoming. We both teach, most of the people on the Yellowbrick team are people who have taught machine learning or taught Python, and so it's a very hospitable, kind, community that's very welcoming of people of all different colors and ages, different genders, and so it's I would strongly encourage if you're interested in becoming an open source contributor to check it out. If you're somebody who does a lot of machine learning and has kind of some interesting ideas for visualizers that don't exist that you think should exist, you should also reach out and propose them as feature requests. And if you're using Yellowbrick and you notice a bug, please let us know. But that's all I have for now, and I think there's a little bit of time for questions.
Yeah, we can take one or two questions. Don't be shy.
Has anybody used Yellowbrick in the audience? Not yet? Yeah. So I would be delighted. It's okay if you don't have questions, but if you're interested in kind of checking it out and reaching out to us. Has anybody here ever contributed to open source before? So not a whole lot of you. So is anybody sort of like, did you kind of maybe catch the bug from listening to Wes's talk? I mean, he makes it sound pretty cool. And I'll be honest, I think that it can be a scary place, it can be a mean place. So if you are kind of hesitant or reluctant, I think you will be pleasantly surprised if you pay us a visit and reach out to us. Questions about Yellowbrick? Or yeah.
On that. Have you played with UMap at all instead of tsnf, and would you want to swap it in at some point?
That's such a good question. And what's funny is that I gave a kind of a proto version of this talk at PyData in New York over the summer, and somebody came up to me after the talk and said basically a similar question, and I said, no, but we don't have that, but that would be an excellent contribution. And he went home and he wrote a new visualizer, and now it's part of Yellowbrick, and you can use it. Yeah, so we do. So you should check it out though, because there's definitely, it's sort of a first, V1 kind of thing, but you should definitely check it out and see if you have ideas for how to expand it. That'd be great. Yeah, great question.
All right. Thank you, Rebecca. So we're going